Okay, in this problem that we're going to look at the cross-section of a plastic channel and determine the position of the cross-section's centroid. So we're going to look at the centroid itself, find out where that is, and then the moment of inertia about the horizontal and vertical axis through the centroid. Okay, so the problem's asking us first to find the centroid, then our I of x and I of y through the centroid. And why this is an important and a good problem to do is because this centroid in mechanics of materials is sometimes called our neutral axis. And that's a real important location for us. It has some interesting properties, which you'll learn about next year. But we also need to know what the moment of inertia is about that centroid. And remember in the short lecture, we talked about this, that the centroid, if we find the moments of inertia about the centroid, that is where we should have the smallest moments of inertia. Okay, so for this problem, one thing we need to do is first kind of define an axis for our problem. And I'm going to assume that this is our x. We need to have some reference axis. And this is our y for our system. So we can now use composite shapes to solve this, right? They're very simple composite shapes. Look in the back of the book. We can use our rectangle, right, for these composite shapes. So first, let's set up this problem to find our composite shapes and how we want to organize it. Remember, there's many different ways we can do it. One is we could set up a shape like this where we'd have 1, 2, 3. Another way we could do it is we could set it up this way and do 1, 2, 3. The way I like to do these sometimes is to look at the whole shape like this and then subtract out this part in here. So now I only have 2 shapes. Right? I just have 1 and 2. And that's how I'll set this up. Okay, so here's the drawing for the layout of this that I'm going to use. We can see that I have the original object here, and I'm keeping my relationship with the original XY coordinate system here, and then I'm subtracting this green shape. And notice I'm showing it 4 millimeters away from that original axis. And that's real important for us because it gives us this relationship. And I've got all the other dimensions on this object. The only thing I'm going to do is I'm going to label this as shape 1, and then I'm going to label this one as shape 2. Okay, let's take a look at this and setting up our normal table that we would have to find the centroid. So remember, we are looking for the centroid first. Okay, so for shape 1, we want to find the area that is just 12 times 32 millimeters, or 384 millimeters squared. For shape 2, we have just 8 times 2, and that gives us 24, 8 times 24. That gives us an area of 192. So if I sum up all the AIs, our total area is, again, 192. And the reason being is this is a negative area, right? We're subtracting that area out. Next, we want to look at our x tildes and y tildes. And remember, the x tilde is the distance to the y-axis, and the y tilde is the distance to the x-axis. Okay, so these both shapes are just rectangles. We know our centroid is located right in the center. This distance is our x tilde. That x tilde is half of 32, or 16. This distance here is our y tilde, and that is equal to 6. So we can place that into our block down below. So for shape 1, x is 16 and y is 6. Now we want to look at the other shape. Again, it's in the center of the rectangle itself. This is our centroid. Our distance for the centroid is, in this direction, is 4. And this value, should be 24. 24. And this distance here is 12. But we need to make sure we add on this additional amount here, 4 and 4. So our x tilde for this shape is this 12 plus 4. Y tilde, the distance to the x-axis, is 4 plus 4. So this is 16 and 8. So again, we have 16 and 8. We don't do anything here. Now I'm just going to use the formula and plug it in. Typically I do x tilde times a for each one and then solve it that way. But let's take a look at that. I'm just going to write this formula out. Okay, so you can see when we use this formula for the x tilde, our result ends up being 16, and for, sorry about that, this should be y bar. We see that our y bar is 4. And let's see if that kind of makes sense. So for our main object here, it is telling us that it is at 16 for x and 4 for our y. So it's right on that surface. And that kind of makes sense for us, right? It definitely makes sense for x bar to be halfway across, right? It's a symmetrical object, so that makes sense. Okay, so now that we know this, we know the centroid, the next task is to find our moment of inertia about the x-axis and about the y-axis. Okay? So let's write this out. We remember that our x, moment of inertia about the x-axis, is equal to ix1 plus our parallel axis theorem, dx1a1, right? That's shape 1. And then we have the second shape, which is ix2. We're subtracting it. Notice that we're subtracting this, right? This is a big negative here. It's a negative moment of inertia that we're subtracting, plus its parallel axis. So we're going to learn about the parallel axis and doing all of this. All right, so if we look on the next sheet again in the back of our book, we can find through the centroid, this x prime, our equation of 1/12 base times height cubed. And I kind of use that always in thinking the base is the axis that I want to go around. So I know that's my base and my height cubed. So let's plug this into our equation. I'm going to write it down here, Ix. Our moment of inertia about the x-axis. So for the first shape, it is 1/12. The base for the first shape is 32, and the height is 12. So we have base is 32, height cubed, 12 cubed. Now we subtract. Oops, sorry. Okay, it's not subtract, it's add the parallel axis. The parallel axis, remember, is this d squared plus the area A. The d squared, though, is the distance to this new location. And the new location that we're looking at for our axis is this x prime here, this new xy location. Oops, y is through the centroid itself, so that's y. Okay, so that's our new location. We know for the large square that it's at this position 6, so we need the distance from 6 to this location of 4. So 6 essentially minus 4, 6 minus 4 squared. squared times the area, which we said was 384. That is the parallel axis part for the first part. And then the second part, now we are going to do the smaller shape number 2. We're going to subtract it. Again, it is, in brackets, 1/12 base. The base of that shape is 24. The height is 8, and that is cubed, plus, now its distance is right here for the shape itself is at this 4 location here, and then we have the distance down. It should be 4 for that location. So 4 squared times its area, which is 192. If we calculate this out, our Ix, moment of inertia about this new axis, the centroidal axis, is equal to 2,048 millimeters to the 4th. Now we need to figure this out about the y-axis. Before I do that, let's look at this. So we've got some value for the moment of inertia about this x-axis, right? And we see we have this material up here and this material down here below it. We've calculated our moment of inertia. Now we're going to calculate about the y-axis. And what do you think it will be? Do you think that value of the moment of inertia for about the y-axis will be larger or smaller than the x-axis? Do you think this moment of inertia about this axis will be larger or smaller than the moment of inertia about this axis? Remember, the moment of inertia is really the disbursement or the distribution of the area away from that axis. So if we look at the x-axis, this is only 8 millimeters away at the most. If I look at the y-axis, right, I've got, 12 millimeters on either side, so there's a lot more away. I would expect the moment of inertia about the y-axis to be larger. So let's see if that is true. Okay, so let's move down here and write our equation. Y for the first shape is, again, 1/12 base times height cubed. 1/12 base, but really the base I always think of as the one we're going around, so it's really height in this case. So that is really 1/12 the base, which will be 12, times the height. And the height for this one is 32 cubed. And then we need to add in the parallel axis to it. So our parallel axis for this one, if we look at it, again, our centroid of the shape is down here, and the centroid of the other one is here. The distance between them, they're both at 16, so our value is actually 0 for our distance. Okay, and our area is still this 384. So there is no parallel axis because it's already there. Okay, so we'll bracket that in. Now let's look at the subtraction part. Let's take the green part and subtract that out. And if I do that, we again have this 1/12, the base, or in this case the height, which is this 8 times the height cubed, which is 24, the base cubed, depending how you look at that. And again, we're going to find that that is 0, right? Because the centroid of this shape is in line with that axis, so it doesn't really matter what the area is. There's no parallel axis there to work out on this. And if we calculate this, our IY is going to equal 23,552 millimeters to the 4th. And you can see from this, this is significantly larger than this one, and that is what I would suspect. Okay, so this was a nice review on being able to find centroids, and then from the centroids to calculate moments of inertia. I do have one more problem that I'm going to do in the next video of a very typical T-type beam.